Next, we have coupled. Coupled is a spatial moment produced by two equal and opposite non-collinear forces. Okay, and that's called a coupled. So two forces produce pure moment. You can think of it just pure moment. So in this case, two forces F and minus F, the sum of the forces, because they are equal in opposite directions, therefore in the line of actions, the force cancel out. But they still have this effect that tend to rotate this rigid body. So let's say we have minus F, that's a distance away from the point of interest O, and F, another force F, that's a plus d away from the point of interest point O. And you can see instead of writing or expressing two force here, we can simply use one moment, this moment here, to represent the two forces. The combined moment of the two forces about an axis, normal two-layer plane, and passing through any point such as O, point O in layer plane, is the couple M. And this couple has a magnitude, let's write it out. So we have a force and a negative force, equal in opposite directions. A cross F and RB cross vector minus F. Okay, minus F. So this gives us RA minus RB cross the vector F. All right, and I shouldn't have done that. Probably let's move this here, a little bit more space. Oh. Right, and this is simply R cross F. Okay, that's what's so special about moment. So point B can be anywhere on the line of minus F and the line of action with minus F, and A can be anywhere on the line of action with the positive F. Okay, and this will be always apply. This is what's special about coupled. Equivalent couples. So here, changing the value of F and D does not change a given couple as long as the product FD remains the same. What does that mean? So let's say changing the value of F and D. In this case, if we compare this one, you see F, positive F and negative F give us the moment, right? The moment. This one, even though D, the distance is halved, and so D is changed, and now 2F also doubled, F doubled. So D and F changed, but the product F times D is the same. D2, D over 2 times 2F, also FD. So the magnitude FD is the same, right? So this scenario and this scenario, they both have the same coupled. You can say that. Similarly, this one and this one, we can keep reading. Likewise, a couple is not affected if the force act in a different but parallel plane. So on top, this plane here, this plane, right? And the bottom, if you imagined, there's a bottom plane right here. It's changed, but they are parallel. The green and the red plane, they are parallel. So the couple, we can say they have the same couple. These are equivalent couples. Similarly, this as well. All right. Force couple systems. A force couple system is a way to describe any system of forces acting on a rigid body in terms of one single resultant force and one single coupled or moment, right? The spatial moment, pure torque, pure moment. So one force, one moment. Here you have one force. In the other way, you can say one force can break down into different, not different, can also break down into one force that goes through the point of interest and a moment. This is what it's doing right here. Because this force is going through point B, so no moment there, but we use this moment to represent the rotational effect of the original force. Okay. All right, let's try this example here. The rigid structure member is subject to a couple consisting of the two 100 Newton forces. They are here, the 100 Newtons and 100 Newtons. Those are the positive and negative F, right? And we want to replace this couple by an equivalent couple, P and minus P at the top, each of which has a magnitude of, so P here is 400, let's write it down. P here is 400 Newtons, right? P is 400 Newtons. And now we want to find what is this angle theta here until it gives us the equivalent couple as the two down here. So let's do that. If you look at the plane at the bottom, this here, right, and we will draw it out, maybe on this side. Each side is 100 millimeter. Okay, we have a force 100 Newton down and 100 Newton up. And M equal to FD, right? So in this case, you can easily calculate 100 times, let's use meters, 0.1 divide by 1,000 is 0.1. So 100 times 0.1, 10 Newton meters. We can say this one here is 10 Newton meters. But I'm going to keep it there for now. Okay. And if we look at this top part right here, now it's smaller. And I'm going to draw it out. Maybe the easiest way is to probably just draw it out. And now this is not to scale, so not to scale, right? But it's also a square with P acting along somewhere along this line, and another P equal and opposite along this line. And we want to find this theta that gives us the equivalent coupled. So let's do that. If I draw the line of action and the distance, now this is a very, very tiny here, my eyes. Okay, that distance there. What is that distance there? We have to figure it out. If this is theta, if that is theta, and this is 90 degrees, so it means when I make this vertical line, here is also theta. Okay, here's also theta. So this case, this distance here, and let's call that dp then. Yeah, okay, use dp. dp is equal to 40 millimeter, which is 0.04 meters, times cosine theta. Okay. So that's our dp. And now we want the two moments to be equal. So what do we do? P dp is equal to F d. And we should write 0.04 cosine theta equals to, 0.04 cosine theta, and then we forgot to times P, which is P is 400, equals to F is 100, D, FD, which use 100. D is 0.1. That's right. Okay, so we can find theta here. Let me use this color. Okay, we can find this theta here. You should get 51.3 degree. So try that. Okay. Last example. We place the horizontal 400 newtons force acting on the lever 200 millimeter long by an equivalent system consisting of a force at O and a coupled. So how do we do that? Well, first we have one force. Now let's create a few more. Right. First, we want a force acting on point O. So the first one, you can say this point O, and the opposite ones. So we are okay. Right, we are okay. Now, this force on top, let me use this one here and this one here. It's a coupled. We can put them as a coupled. Okay, so I should put this lever here. Okay, we should get rid of that. Right, we should get rid of that. So now, if we put that as a coupled, then the only force left is this force plus a moment. Can you see that? perhaps we can use the green because I circle this in green, this one and this one. So let's use green moment. And what's the magnitude there? Well, m equal to Fd, and that F is 400 Newton. The D, the vertical distance, right? It's this vertical distance right here, from here to point O. So that would be 200 sine 60, okay, or 0.2 meters. 0.2 meters sine 60 degree. That gives us moment, I have 69.3 Newton meter. Okay, Newton meter. All right, so the last point here I want to make is the reverse of this problem is often encountered, meaning if we have a moment and a force, and now how do we combine this moment here, right? This moment and this force into one single force, or the reverse, you convert this moment back to this using equal and opposite to F. And of course, for that, with the moment, we also need another one, F up here, where we don't know yet, but we can calculate and make those two equal so they cancel out, right? Make those two equal, they cancel out. And the moment arm for the second force, for this top force here, has to be moment divided by this magnitude of this force, which is now the ratio should be 69.3. That's what we calculate. Okay, divide by 400 newtons. So the moment arm, this vertical distance, this vertical distance here, right? If you calculate that, it should be 0.173 meters or 173 millimeters. And because of the angle, you got the angle, right? We can calculate the length along this line here. Let me use red. The length along this line here, and you will be able to find that at 200. That's where you can locate the force. Right, that's the line of action. Oops, this oops, right here, this line of action. Okay, so that's it for lesson 3, and hopefully this is okay, and I'll see you next week.